Alright, in this video we're going to be talking on elimination reaction versus substitution reaction of alkyl halides. Now, alkyl halides could either undergo elimination reaction or substitution reaction. Those are the two major reactions which alkyl halides undergo. Now, these two processes will most likely occur simultaneously, leading to the formation of a mixture of products. One most likely a substituted product and the other an eliminated product. These two products compete during this reaction, and at the end of the reaction, one of the products will predominate while the other becomes less dominant, just as I've read earlier. Now, alkyl halides could either undergo substitution reaction or elimination reaction. Now, for you to understand this topic, I just want to give an example of something you might have done previously, so this won't actually look complex. Now, just like in chemical equilibrium, the forward reaction always competes with the backward reaction, and at the end of the day, one of the reaction predominates. Not that that reaction actually produces its product 100%. It predominates. That means it's of a higher percentage compared to the other one, and that's just what's happening here. But instead of the forward reaction and the backward reaction competing here, we have elimination reaction competing with substitution reaction in alkyl halides. Now, when substitution reaction and elimination reaction are competing, the chances of elimination reaction occurring increases from primary alkyl halides to tertiary alkyl halides, and that of substitution reaction decreases from tertiary alkyl halides to primary alkyl halides. Now, what this point is just trying to say is that primary alkyl halides will likely undergo substitution reaction easily or more readily compared to tertiary alkyl halides, while tertiary alkyl halides more likely undergo elimination reaction. Now, this is an important point to take into consideration, because if you're dealing with a tertiary alkyl halide, you have to know that tertiary alkyl halide will most likely undergo elimination reaction, so you won't end up wasting your time trying to get a substituted product. You could still get substituted product depending on the type of nucleophile you use, but most likely it will rather undergo elimination reaction rather than substitution reaction on a normal basis. So that's what this point is actually talking about, and is a really important point, so please take into consideration. Now, for example, primary alkyl halides yield alcohol more readily than secondary alkyl halides, while tertiary alkyl halide hardly yields alcohol by nucleophilic substitution. Now, we all know that the conversion of an alkyl halide to an alcohol, that is the Cl or the X minus group, depending on the halogen you're using, you're converting that X minus group into an OH minus group. That's the hydroxide group. That means you're converting from an alkyl halide to an alcohol. It's a substitution reaction because the halide ion will end up being replaced by the OH ion, and that will end up leading to the formation of an alcohol. So that's a substitution reaction. Now, like this point I gave, primary alkyl halides will yield alcohol more readily than secondary, while tertiary will hardly yield alcohol by nucleophilic substitution. While tertiary alkyl halides yield alkane more readily than secondary, and primary hardly yields by nucleophilic elimination. That's just like the reversal, but this is like elimination. That's the pi bond actually comes and bond with the sigma bond, and then leads to formation of an eliminated product, an alkane. Now, please note, it's not that primary alkyl halides do not form eliminated products or not form eliminated alkanes. They do form it, but they hardly form it. It's not easy, and a factor that it could actually depend on is the nucleophilic reagent used. That's like the major factor that all these reactions depends on, the nucleophilic reagent used. So now, if you use a different nucleophile, you will find out that primary alkyl halides could still undergo elimination reaction, and elimination reaction could easily still dominate regardless of the point I gave. But on a normal condition, it rather undergoes substitution reaction than elimination reaction. Now, we're going to be talking on the first group of nucleophile, or what should I say, the first type of alkyl halide. Now, the first type of alkyl halide we're actually going to be talking about is primary alkyl halide or 1-degree alkyl halides. Now, primary alkyl halides could either undergo SN2 or E2 in the presence of a strong nucleophile. Now, like I said, I've not given this point, but let me just tell you. Now, the factor which all these reactions actually depend on is the nucleophile you actually use. Like chemical equilibrium, the example I gave earlier, chemical equilibrium depends on the temperature, the concentration, the pressure in gases, and volume, and other factors. But in alkyl halides, elimination reaction versus substitution reaction, what it actually depends on most of the time is the nucleophile. Note, it could also depend on the point I gave earlier, that is tertiary rather undergoes elimination and primary rather undergoes substitution, but the major factor that it depends on is the nucleophile. Now, like the point I just gave, now what mainly determines the product formed is the nucleophilic reagent used in the reaction. Now, SN2 reaction is mainly favored by the presence of good nucleophile. Examples of these good nucleophiles are the halide ion, that's either the iodine ion, the chlorine ion, or the bromine ion, the cyanide ion also, and the RO group ion. Now, don't be confused because there's nothing in chemistry like RO group, RO minus group. It could be there, but it's not really like a major group. It's a family. I can say the family of alcohols and others. We can call them this family. But let me just give an example because I just didn't want to give a long list of nucleophiles which end up confusing a lot of people. So I just classified all of them as RO minus group, mainly because they have the RO group present in the nucleophile. Now, this RO minus group include alcohol, carbonyl group, ethers, carboxylic acid, and esters. Now, carbonyl group, like if I'm trying to classify the O family, carbonyl group shouldn't be there, but I just put it there, so that's why I'm not trying to claim this is like a particular group. This is not a particular group. Now let me just give the structures. Like RO could either be ROH, that's for an alcohol. For a carbonyl, you know there are two different types of carbonyl, so it could either be a ketone or it could be, so there are two different types of carbonyl. So let me just go on and talk about that. Now, the carbonyl groups that we're actually going to be talking about, let me just classify all of them together. That's RC. Then this C will end up having a double bond, and this double bond could be an O, it could be an R, or it could be a H. So ROH, depending on the group we're actually talking about. Now, it could be an ether, the ROR group, also a carboxylic acid, the carboxylic R, the RC double bonded with O and single bonded with OH. Now, what this group, I just classified all of them together as one, so don't get it confused. So now, but E2 is favored by a stronger and more bulky nucleophile. Now, E2 is not favored by the factor, like E2 is favored by a stronger and more bulky nucleophile compared to the nucleophiles which I gave earlier. They are strong also and they are good. A2 is favored by a stronger nucleophile and a more bulky nucleophile. From the name, you can actually see it. That's tet butoxide. This is a stronger and a more bulky nucleophile. I would have given you the structure if I had, but don't worry, you could just actually decode it. I'm sure I really explained it well. So let's just go forward. Now, I'm actually going to be talking about, I'm going to be giving an example on all the points I just gave earlier. Now, the example I'm using is a primary alkyl halide, and the primary alkyl halide which I'm actually going to be using, as we can see, is butyl bromide or bromobutane. Anyone you want to use, but we'll be using butyl bromide for this example. So let's just go on. Now, like I said earlier, SN2 is favored by good nucleophiles, and what E2 is favored by tet butoxide nucleophile. That's the only nucleophile that favors E2 for primary alkyl halides. So now, the good nucleophile we'll actually be using is the ethoxide ion. The ethoxide ion is an ethyl with a binary group, or it could be any other group. It could also be, just the ethoxide ion, because all those groups, like an alcohol, could also remove its hydrogen, and it could be an ethoxide ion depending on that's an ethanol, or depending on whatever group it is. So the ethoxide ion is the nucleophile I'm actually going to be using. So now, as we can see from the example that I actually gave here, when butyl bromide reacts with the ethoxide ion, it produces butane. These are the two products that will be formed in the vessel used. That's one butane and butyl ethyl ether. Now these two products, they end up competing for which will predominate and which will become less dominant. And at the end of the day, as we can see from the percentage level that I actually gave here, butyl ethyl ether, that is a substituted product, ends up predominating, while one butane, that is an eliminated product, end up becoming less dominant. Now, when this butyl bromide again is reacted with tet-butoxide ion, what actually happens is that the one butane, because that will still be the product that will be formed, the one butane would predominate, as we can see from the percentage, while the ethyl tet-butyl ether, that's the substituted product that will be formed, will become less dominant. Now, like I said earlier, the two products will still be formed, but one will predominate and the other will become less dominant. One will be produced in higher proportion compared to the other, and that's just what's happening here. So that's just everything I'm talking about here. So now let's go to the secondary alkyl halides. Now let's talk about secondary alkyl halides. Now secondary alkyl halides could either undergo SN1 or SN2 for nucleophilic substitution and E1 or E2 for elimination reaction. Now that's just, they could either undergo any of these two reactions. That's something about SN2. Like I said earlier, SN2 is completely dependent on the nucleophile used, because they could either undergo SN1, they could either undergo E1, they could either undergo SN2, either undergo E2. So it's solely dependent on the nucleophile you use. Now for SN2 and E2 reaction, the basic differentiation factor is the type of base used. Now, the base I'm actually talking about is Lewis bases. We all know Lewis bases are electron pair donors. So now, if you use a weak Lewis base, that's if you use a liquid Lewis base, it will end up favoring SN2 reaction. As we can see, weak Lewis bases favor SN2 reaction. An example of those weak Lewis bases, now we can see, is acetate ion. Now, strong Lewis bases favor E2 reaction. An example of that strong Lewis base is ethoxide ion. Now, SN1 and E1 usually occur in the presence of allylic or benzylic alkyl halides. That means they are mostly particularly formed when a benzylic or an allylic alkyl halide is present in the structure. What that is just trying to say, that point just trying to say is that a secondary alkyl halide, this is the C, and at the end of the day, and this is the alkyl halide, the X group. Now this other group, because it's a secondary alkyl halide, we all know that it's meant to have two alkyl groups and one halogen group. Now this alkyl group, it will end up becoming either a benzylic group, that's this a phenyl, and that will end up becoming a benzylic group, or it could become an allylic group. We all know what an allylic group is. That is the resonance structure of a propyl, and that's just what the two groups that will actually be formed, and that is where SN2 and E1 reaction mostly predominates. Otherwise, SN2 and E2 predominates. Now, SN1 and E1 are favored by the presence of weak basic nucleophiles in the presence of solvents such as acetic acid and ethanol. Just like the point I gave earlier, SN1 and E1, they are mainly found in allylic and benzylic alkyl halides, whichever one. And SN1 and E2, now the nucleophile that actually favors them is the presence of a weak nucleophile in the presence of solvents. That means the weak nucleophile is not just acting alone, it's going to act in the presence of solvents such as acetic acid and ethanol. That's what favors SN1 and E1. But now I'm going to be talking about SN2 and E2 because those are the two major reactions that actually predominate. And in this, I'm talking about alkyl halides. Maybe in the next video when I'll be talking about benzylic and allylic, that's all those resonance and conjugated halides, I will actually be talking about SN1 and E1. But now I'm talking about primary, secondary, and tertiary. That is simple structure and chain structure. I'm actually going to be talking about SN2 and E2 only. So let's just go for. Now, from this example, we can actually see a bromopropane. That's 2-bromopropane to be precise, actually. Now, like I said earlier, the 2-bromopropane could either undergo SN2 or E2, depending on the nucleophile used. Now, the first nucleophile is a weak base. That's a weak Lewis base, and the weak Lewis base uses acetate ion. Now, this acetate ion will end up undergoing substitution and elimination reaction. But as we can see from this example now, it's meant to produce an eliminated product and a substituted product. But at the end of the day, we end up not getting an eliminated product. That means this reaction is completely a substitution reaction. An eliminated product will end up not forming. This is meant to be the eliminated product that will be formed, but at the end of the day, we end up not getting the eliminated product and we end up only getting isopropyl acetate. Now, when the 2-bromopropane react with a strong base, our strong base being ethoxide ion, it ends up producing like a substituted product and an eliminated product. Now, the substituted product that ends up forming is ethyl isopropyl ether, and the eliminated product that ends up forming is propane. Sorry for the R, it's actually propane. And now, just like the example I gave earlier, we can see that the propane actually predominates while the ethyl isopropyl ether becomes less dominant. And that's just all for secondary alkyl halides. So now we'll be moving to our next one. That's the last one we're actually going to be talking about, tertiary alkyl halides. Now, tertiary alkyl halides undergo E1 in the presence of bases such as OH or RO-, but could undergo SN2. Now, there's something we need to note. Like I said earlier, tertiary alkyl halides, in my previous video, I actually mentioned this, that tertiary alkyl halides mostly undergo E1 and SN1, but now we can see that tertiary alkyl halides could also undergo SN2. That means nothing is constant. I'm not saying they mostly undergo those reactions, but we can see it's not a mistake. They could also undergo SN2 reaction. That's just what I'm just trying to say, that nothing is a coincidence. They could undergo SN1 and they could undergo SN2 regardless, just dependent on what happens. The reason that I gave it that they undergo SN1 is because they mostly form a stable carbocation, but another reason why they can't undergo SN2 easily, like I said earlier, is because of steric effect. But if they are able to, now, I don't want to be talking about that in this video, but let me just continue. Now, if they're able, if the nucleophile is able to find a point of attachment at the back of the primary carbon, let me just illustrate with a diagram so you understand what I'm talking about. Now, let's say this is our tertiary alkyl halide and these are X group. Now, we all know that they could form a stable carbocation. That means this group will end up leaving and giving it a positive charge. And at the end of the day, when this group leaves, we'll have this as our carbocation. This is what I mostly talk about. It could not either undergo SN2 or E2. SN1 or E1. But when this happens, that's just like the major reaction of that. But now, regardless of that factor, if I put this X group back and I remove the positive charge that makes it a carbocation, now regardless of that factor, they could either undergo SN2, like we can see from what I'm talking about. That means the nucleophile could actually still come if it could withstand, or what should I say, break through all these steric hindrance of all these bulky groups. It could still come and bond here, and at the end of the day, it will lead to the formation of a product formed by substitution, elimination. Nucleophilic substitution by molecular reaction mechanism. So that's just what I'm talking about. So now these are the two major reactions they mostly undergo. So let me just keep talking about it. They could undergo E1 or SN1 under non-basic conditions. Examples of those conditions, under non-basic condition, example of those conditions are heating in the presence of ethanol yields a mixture of product from both E1 and SN1. Now that's just the first one, and this ethanol that you're meant to be heating, it's meant to be a pure ethanol. Now, for example, 2-bromo 2-methylpropane, that's the example I'm actually using, and that's what I'm actually going to be talking about like further on. This is the example I'm using, then I'll show you the structure and everything later on. But now, for example, 2-bromo 2-methylpropane gives a higher yield of elimination products when treated with ethoxide ion in ethanol, but under non-basic conditions, heating with pure ethanol, substitution reaction products predominate. That means under non-basic condition, and that non-basic condition is heating with pure ethanol, 2-bromo 2-methylpropane will yield to the formation of a substituted product. So now, the example I'm actually talking about, I'm sorry about that. So now the example I'm actually talking about, this is it. Now this is a 2-bromo 2-methylpropane, as we can see from the structure. Now when we heat with ethanol in ethoxide ion, we end up leading to the formation of a substituted product and an eliminated product. But as we can see, the ethyl butyl ether, that is the substituted product, ends up becoming less dominant. Only 3% will be formed, while the eliminated product, that's 2-methylpropane, will end up becoming more dominant compared to the ethyl butyl ether. But in the presence of pure ethanol, that is in the absence of ethoxide ion, the first was ethoxide ion in ethanol, but now in the absence of ethoxide ion, that's pure ethanol, the ethyl butyl ether, the same product formed, will actually predominate with 80% compared to the 2-methylpropane, which will become less dominant with 20%. And that's just the 3 examples I'm actually going to be talking about. So thank you for watching this video. Please like and subscribe to my channel for more of these videos explaining organic chemistry. Thank you. Have a lovely day.